Hello, everyone. We're just making a little bit of time to buffer the attendees here. So welcome to the presentation, and I'm looking forward to being your guide and host for today's webinar. In the meantime, just adjust and let's give a little bit of time here for others to start logging in there here. I'll be here and probably entertaining you or just annoying you for the moment. A few more seconds and I think we're ready to start. Okay, that said, this webinar is presented by EDB, Enterprise DB, and the title is, if you already know, what are asset properties in Relational Database Management Systems? A few housekeeping items here to keep in mind. Our slides and recording will be available within 24 hours. Feel free to reach out to us. Any questions that might be left out at the end or not answered, we will be glad to help you answer them just by having you reach out to us and be in contact. We will also be taking care of the questions at the end also. And any others, as mentioned before, they will be answered, rest assured. That said, let's get started. A little bit about me. My name is Doug Ortiz. I'm a senior Postgres DevOps engineer with Enterprise DB. I have a variety of experience, among them multiple technologies and platforms, among cloud, big data, data science, data analytics, DevOps, platform engineering, multi-cloud software, etc. But not going to bore you in great details with those, which you probably already know. You can reach out to me just by looking down here in my entire area of what I'm going to be working with. You can see my GitHub is there. You can see also my Blogspot and my video YouTube channel. Feel free to reach out in any of those means there that you might have as well. Well, our agenda for today. I'm first going to be briefly introducing, revisiting, rediscussing what ACID is, the properties, and the whole reasoning behind it. That'll be leading into the four different distinct properties themselves: atomicity, consistency, isolation, and durability.
Hey, Doug, sorry to interrupt, but I don't know if you're sharing your screen.
Oh, one moment, please. I might have had a technical difficulty here. I'm going to start sharing my screen. Okay, hopefully that takes care of it.
Looks great. Thanks, Doug.
Thank you. Sorry for the mishap there. So I'm not going to be repeating everything else we talked before. We talked about what the theme of the title of the webinar is, the recordings, along with the questions, a little bit about me, and we're already talking about what's going to happen around the demo. That's where I was leading into. The demo will be a brief, around 6 minutes, and we're going to take a look at in details of how we can apply asset properties, examples of those, and ideas around them. They're not one single answer for everybody, but they will at least give you some ideas and spark interest in there. Last but not least, we're going to have the takeaways along with how we can maximize the application of asset properties in Postgres, and ending with a Q&A. So let's go ahead and get started. Let's start reviewing what asset properties are. They are of great importance, obviously, because they are the reason and the mechanisms on which you can keep your data consistent, available, reliable in your relational database management system. There are multiple RDBMSs out there: Postgres, SQL Server, non-SQLs as well, but many of those, you have Oracle, one of the major ones as well that everybody's heard of. All of these rely on some sort of asset properties. Which ones? ACID stands for atomicity, consistency, isolation, and durability. Each one of these four are the properties. It's easier just to remember them as ACID, ACID. They ensure the whole idea and goal of these properties is to ensure that the data is reliable, consistent, valid at the beginning and end of any change in the database. Recoverable, recoverable at a point in time. All of these are the characteristics that we're looking for and we expect from ACID. So let's start with a definition of atomicity. Atomicity is pretty simple. Putting it this way, atomicity starts with a transaction, a block. This transaction can have multiple statements in here. Those statements, all of these will be executed. It's all or nothing. Simply like that. It either all works, it's indivisible, and that is one of the big things to keep in mind. We're going to have characteristics for each one of these properties. And the characteristics are, for atomicity, 3. Indivisible, which I mentioned before, meaning all of the transaction has to occur. If there's an error in between the entire transaction, any of these steps in here, none of these will execute at the failure. They will also be consistent, meaning that they will be reliable. They will occur. Once the transaction has fully completed, it will be available for everybody else, whatever the changes were. It'll also be isolated, meaning there can be many transactions here, but each one of them will have a point in view of the data they are changing, accessing at a specific point in time. Okay, how is this achieved? This is achieved by transaction logs. They're known by a few names, mostly as redo logs, in Postgres particularly the WAL, the write ahead log. These are written. So let's have an idea as if there's a transaction, this is your log, there's going to be multiple occurrences, commits, changes, etc. They will be kept in track in here, each one of these. The whole point of this is that if something occurs, a disaster, or there's a reason to roll back, again, the changes, you can do so. That's one of the roles. It's durable and recoverable. You can undo and rollbacks, and in case you need to do it, you can reapply again. I apologize for my drawings here, they're pretty bad. But that gives us an idea of what the role of transactions end up being in atomicity. A few real-world examples. Fund transfers, bank accounts. That's probably the easiest one you can think of. Whenever you're having a transaction occur at your bank, you definitely depend on the values, on the whatever was deposited or removed, or the checks that were processed. If they are not updated properly, your balance will not be proper. You will not have funds in there, and that's not good. They should supposed to be atomic. It works all or none. Let's say, for instance, you have 3 checks you went to deposit. One of $10, one of $20, one of $30. Well, each one of those should be atomic. They go through all or nothing at the same time at the end. Because if not, you don't have any reliable data. Another real-world example is e-commerce. E-commerce is usually will have a few steps. You make the request that you want to purchase something, then you check the inventory, and then you make the purchase. Those 3 steps should all be sequential first and reliable. Why? Because they have to get paid, they have to have inventory. And once they perform a sale, that information should be available and reliable in those 3 steps. At the end, the inventory should be entirely reliable. In case somebody else wants to purchase more of their inventory, it should be there and reliable. The number should be exact. Otherwise, it's going to fail. It's never fun whenever you hear those cases when somebody goes online and they bought something they thought was in stock, and it turned out to be that it was not. Another item where we all have experienced reservation systems, whether it's flights or hotels, to prevent overbooking. If there are no more rooms, you can't stay at the hotel. If there are no more seats for the flight, you will not have a reservation system there that it's accurate and reliable. And that is not good for business. In the end, everybody knows that. Okay, that leads us into consistency. We have a definition for it. Meaning is whenever a transaction occurs, we have the transaction itself. It should be valid before and at the end, with all the data in between being consistent in here, all of it. Rules, constraints, no anomalies, no inconsistencies, meaning hopefully no nulls, no negative values in case of inventories, no incorrupt data there. That's what we're trying to achieve. That's what the consistency in asset it looks to achieve. What are the examples that we can really take into account? Well, let's see. We have consistency being accomplished by constraints, triggers, keys, unique constraints. All of these target one thing: validity of the data, consistency of the data, reliability of the data. For instance, any of these could be done via keys, triggers, and that can be accomplished in one of the methodologies as mentioned here. A primary key would be unique. The whole point of a primary key would be to have consistency in which a key is not duplicate. Then you would have a foreign key. The foreign key should be able to reference the primary key that we have previously established. And constraints, those could be as simple as something that's not allowing nulls, negative values. Those are few quick examples that come to mind. And triggers, these could be used after some data has been updated, deleted, cascaded deletes. A lot of people don't like those because they can be tricky and delete data and be hard to recover at times or just follow up, but they can be used in a variety of manners just to keep your data consistent and reliable. The next property is isolation. This one really figures one simple way. We have a transaction, multiple transactions, and the data that's available for each one will be at a specific point in time. There's multiple ways and multiple levels of these, meaning each transaction will have a snapshot, and these will vary based on your RDBMS itself. Let's take a look in more detail of what I mean by the levels there. You have 4 levels. The recommitted, meaning you will see only the data that's been committed. The repeatable read, it's a consistent snapshot throughout your execution of a transaction here. So, and serializable, they are one after each other. Now, the last one, read and committed, is not supported in Postgres, but other RDBMSs might and can hopefully support them as well, meaning you can access uncommitted data in other transactions. Now, keep that in mind. That could lead to data conflicts and can impact your data, which is the next point of our slide deck here. All of the data that's visible, modifiable, has performance trade-offs. What is available for a specific transaction can lead to conflicts, meaning any of these maybe they get the data at a specific point in time, from the beginning. But if it's not the same snapshot or reliable at that level, it could lead to conflicts, issues. Now, there's techniques for that. There's trade-offs. Higher isolation levels can increase the locks or unreliable information or serializability of transactions. Meaning your transactions, if they're serial, they will be executed in a specific order and one after the other. And that's okay. But you have to be aware of these impacts, of these levels, how they affect your application, your database, and how you present that data to your end users. As mentioned before, there's techniques for isolation, locks, OCCs, MVCCs, snapshot isolation as well. For example, locks is a way of having a transaction take a snapshot of a record here and hold it. So this gets held. Nobody can access it. If there's multiple calls for it, that could be an example in Oracle, they will not be able to make a read, update, etc. until it's released. Once it's released, others can access it. Optimistic concurrency control assumes that any lock is rare, but prevents any other access to a transaction from exclusive locks for updates itself until it's released. That's one of the problems. These, as mentioned before, the conflicts are rare, but also it doesn't acquire locks. But then you have more conflicts, trade-offs again. You have any of these trade-offs being there. Postgres leverages a lot what's MVCC. You can see a consistent snapshot at the start of the transaction. So I'm going to showcase that here. So you have a transaction and you get a snapshot at the beginning. If you have multiple ones, different points in time will have different ones. Nothing wrong with that. That's just something you have to plan accordingly. That happens in MySQL. That happens in Postgres itself. It takes each one of those snapshots themselves. Then you have what's snapshot isolation, meaning snapshot isolation is for each transaction, a snapshot is taken at the beginning of that specific transaction. You can have many, but it's going to be at a specific point in time in there. Nothing wrong again. They're just different relational database management systems, and they work separately in different matters, depending on your cluster, your architecture, your version, etc. Okay, trade-offs. We were talking before about these trade-offs. Higher isolation levels will provide stronger, consistent guarantees, but on the other flip side, it may lead to more blocking and decreased concurrency. And then if you lower those isolation levels, you're going to have higher concurrency, but dirty reads and non-repeatable reads. Your data might not be that accurate or as accurate as you would hope it to be. Again, that depends on what you're trying to achieve. Each application, each piece of code will vary, will differ based on what your industry, your goals, and your application itself are. Great. That leads us into the following item, durability. Let's see what the definition of durability is. Durability ensures that any changes are permanent and that they can survive any recovery, any disaster. Why? Well, of course, we talked about the transaction logs before. If they are not recoverable, if you make a change and you cannot recover, redo it, undo it, then how reliable is your entire database? That's the whole point. The logs make the changes, and ensure that they are recoverable from them. Any change there. This leads to what it can encompass. The write durability, as we see here, and then the crash recovery. Any write should be stored reliably and recorded so that you can recover from it, undo it, roll back from it. No matter if it's a hard HDD or an SSD, whichever type of format you have of storage. That's the whole point of it. And then crash recovery, of course. If a disaster occurs, logs should be able to roll back to that last point in time, or even further back if you need to. Keep that in mind. This is achieved for durability through the following mechanisms. Mentioned before again, transaction logs. And the key aspects of those are your log records, your wall. All of these are captured sequentially and keep going one by one, meaning each commit, each record, you will be able to move back and forth if you want to go to the beginning, middle, or any point in time. That's the whole idea behind it. It gives you options to recover that data, no matter where and when it happened. How do you maintain durability? Transaction logs, by committing them or uncommitting them, but most importantly, your ability to have checkpoints. So let's say you have your log here. There will be specific points in time that you'll be able to recover from. These are checkpoints. From the entire process here, you have choices. Those checkpoints are what give you that availability of choosing where and where you want to recover your data from. We move into the strategies that you can take for your durability here. There's multiple of all these. Your full backups, your incremental, your point-in-time recovery, hitter, your recovery point objective, RPOs, replication, high availability, but most importantly, the last one. Make sure and implement and test your disaster recovery procedures and plans. We're going to come back at the end of this slide deck again on that one because there's a lot of key items to consider. Full backups. They can take as long or as little time as the size of your data. If you have petabytes, guess what? It's going to take a while. That's where that leads into incremental backups. You might want to have full backups at specific times where there is not that much access to those database, which will allow you to have incremental backups. So your full backup encompasses everything, but an incremental one has kind of similar to the idea of the checkpoint. You have from the beginning of the full one, then you have a specific point in time aggregated data that you can choose from. Of course, those incremental backups will execute faster because they're additional. From the entire whole instead of everything, you have just additional data being aggregated there, which leads to the point-in-time recovery, allowing you to choose if there's a disaster, a date and time, and depending when those incremental backups were performed, along with the logs and the checkpoints. Leading into the RPO. An RPO stands for your recovery point objective. Bottom line, the short story of it is, how much data can you lose for your business to continue operating? So if you have your entire set of a backup here, but there was a failure in this area here, is this good enough for us to continue our business? All the data between here and there was lost. Maybe it was an hour, maybe it was 2. Do we know how much we can afford to lose? Do we know how much we cannot afford to lose? Maybe it's as little or maybe as much. That varies by industry, organization itself. That's no single answer for that one. Replication, that's going to be depending on how is your environment set up for. Maybe you have replication occurring to another cluster between your relational database. And once it happens to be severed, you can have a load balancer here that's always been checking to see if they both were available. And your data would access that load balancer, determine, okay, this connection has been severed, it went down here. Hey, I'm not going to lead the traffic anymore to this server, going to be redirected to the other one. That's one simple way of keeping your business continuity live. And also high availability. Those two go hand in hand. Doesn't mean they have to, but that's one of the ways you can architect your data being available. And last but not least, as we were talking before, many organizations, you'd be surprised at the size of them. You would imagine this never happened, but I've been part of many disaster recovery procedures, and some have been really bad to the point that there were no reliable backups going from full to incremental. Why? Simple answer, they never were tested. They had a plan, disaster recovery plan, that was just word of mouth. You make a backup, we'll recover it. It'll work. Keep in mind that if that backup doesn't work, if your full backup, you don't have any full backup, and then the incremental ones, you're kind of stuck in whatever that data was lost at that point in time. So if none of your full backups are reliable, it doesn't matter if your incremental ones are good. You've lost all that data. That's as simple as that. Sadly, that is a scenario that happens sometimes. Not often, but it happens sometimes more than you think. Okay, that leads us into demo time. Let's go ahead and take a look and see what we can look and share here. I have a demo that we're going to go through. We're first going to take a look at Atomicity. With that said, we're first going to create a database called aptly named ACID. And this is Postgres. As you can see, it's version 13. We're going to first list where our scripts are located at, and then see what is available for us. And of course, we have a few scripts available to us. We have the Atomicity one. So let's take a look at the SQL script itself. Let's see if I don't make a wrong mistake there, and I did. So let's take another approach for looking at the SQL script. And this should work, hopefully. So the first thing is we draw up our table, just to make sure that there's nothing there. We have the structure of the table is an account number, and it's a serial primary key. And it has a balance column. We're going to insert 3 values, 1,000, 500, and 2,000. Then our transaction will start, as we'll see here. This is the entirety of our transaction. It begins and gets committed. Everything that happens in between the commit and the begin has to work successfully. It's indivisible, all or nothing. Meaning, if anything fails within this transaction fails, we should still have those 3 balances there. Let's go ahead and see if that's the case. I'm introducing, as you can see here, an error on purpose to make the transaction fail. And the other 2 should work successfully if there's no error. So let's start that process. Let's execute the transaction, script file, type it in, and execute it. But first, let's reconnect to the database and execute properly now. Notice it failed, as expected. I introduced a division by 0 error, as I showed before, meaning it caused an issue and we only got the inserts. We didn't get to work any of the statements in the transaction itself. We have the table, and we're going to check for the values there. They match exactly to what our code was performing, the scripts were performing that SQL statement. So let's go ahead and remove that error now. Let's go look for it and comment it out. Let's execute again the script and see if this time it succeeds, which it did. Successful update. We had the drop of the table, created the table, 3 inserts, began the transaction, 2 updates, and a commit, meaning the data should be different now. Now let's take a look, compare top versus bottom. It changed because it executed the updates, 2 updates we requested to be done. They are both successful. And that's the whole idea of atomicity, indivisibility for that transaction itself. Now let's take a look at a consistency here. We're going to, again, connect to our asset database. And let's look at our scripts, list them, and look at the content for consistency. So we drop, as usual, the table. We create the table. And then we insert a tuple in the employees table for John Doe with a key of 1, followed by Jane Smith with a key of 2. But we're going to insert a duplicate key here. And this should fail because we want to keep the keys consistent. There should be only 1 key value there that it's valid. So let's check and see what happens when we execute the script. There we go. It failed. A duplicate key value. It violates the unique constraint that we defined on the table itself, on that column, the key column. Let's look at the code once more. We had a consistent John Doe value with key value 1 and Jane Smith, but the third one was expected to be fail itself. And that's great. Consistency at work. Now let's take a look at isolation. That's a bit more abstract, but hopefully this should exemplify what we're trying to accomplish. And once more, we connect to the database. We list our scripts. And we start looking at our code here. It's pretty simple. We create a table orders. And notice we have a repeatable read in the transaction at the beginning. So there will be a snapshot unique to this transaction itself. There's going to be insert. We're going to get the select the values, going to perform the commit. And that means that after the commit, the change should be recorded. Let's take a look. It's comprised of 5 steps here. Let's check to see if it's clean. We don't have any tables, so we can reliably execute the script. And yes, it successfully worked. We have a positive and successful execution there. Time to check durability, last but not least. Once more, we connect to asset database. We list our scripts. And we look at the code here. We drop the table in case it's just a simple message table. We look at the transaction comprised of 4 steps: the begin, the insert, the commit, and another select. The whole idea here and the goal is to show that it was persistent and it's there no matter what the value, even if it's false, as we set it by default there. So let's check to see if there's any data, no tables, and let's execute the script. We get the error that it did not exist, but that's to be expected. And we see that it was inserted and committed successfully for both. The data saved there is the same. We didn't make any changes, which means everything was successful. We can go back and cross-check. We just didn't insert. We didn't do anything else. We didn't perform any updates or deletes. that would take care of our demo for today, leading us back into continuing our takeaways. Let's take a look at those in more details. Maximizing ACID in Postgres. Recommended to use transaction. All of your operations should be beginning and ending with your transaction there. You should also define constraints. And why is that? It helps you have the consistency of all your data there. It really does. When you do that, you're able to see what is happening. Then you can optimize your database design. Let's go back to my screen here to share. Sorry about that. So we're back here. As mentioned, utilize transactions, leverage them as much as possible. Then define your constraints, primary keys, foreign keys, triggers, anything that allows you to ensure that your data will be reliable, it's valid, and optimize your database design. Why? Because as we already talked before, that leads into isolation levels. You're going to be able to handle and have trade-offs there, or handling your concurrent access. That will determine, all of these will go in hand. Your isolation levels, your database design, will lead into concurrent access. Not forgetting about your error handling and rollbacks. Always implement error handling mechanisms within your SQL code and whichever code accesses and executes any statements within your database. Of great importance, and not to forget, backup regularly. Test those backups. Make drills. You'd be surprised that once a disaster occurs, panic ensues. It's hard to focus, and it's so much easier to have just a checklist of what is needed to do step by step and in great detail. Because once panic sets in, it's very hard to focus, think clearly, and that helps you to prevent second guessing yourself or second guessing anybody else. If you perform those drills regularly, it'll accelerate and prevent a lot of downtime for your team and the entire organization. Monitoring, of course, you need to be able to monitor and verify things are working properly, databases up and running, and tune it right there. Perform and handling scheduled tuning performance of your database, whether cleanups, maybe you want to clean up data, clean it up, etc. Keep up to date with your Postgres releases and updates. That varies by organization, but one thing that is unofficial or de facto usually is most organizations don't go for the latest version or update. They stay with a -1, give or take. That's more or less the consensus I've seen around. Along with disasters, planning and documenting them. And again, recovery drills. That's really the key to all of this. Next are references, in case you're interested. Not only with the slides, I've had a lot of these information here provided to you via these links that were kindly provided by others in those websites provided. And that said, let's take a look at the Q&A. Start that. Not sure if there's any Q&As, questions there, but. Ready and listening here. If you have any questions, feel free. Unless you don't, and I'm hoping and guessing that there are no questions. Hopefully it was clear enough. And I think it's might be a wrap then, if we don't have any questions.
Thank you very much, Doug. I'll be sure to share the recording and slides, if not today, then tomorrow. Thanks everyone for joining, and have a good rest of your day.
Thank you. Bye.